So there are few things more important in a molecular biologist's toolkit than the polymerase chain reaction. So before you hop into the laboratory to do some PCR, I think it's really important that you take a little bit of time to just think about and visualize what's going on in that thermocycler and in that little microcentrifuge tube that you're going to be using. So the magic of the polymerase chain reaction is that from within a very complex mixture of DNA, genomes are huge, we can target using primers, specifically designed short DNA fragments complementary to one small region of the genome here. We can target one specific region of the genome and make so many copies of it that now we can see it when we run a gel. So that is the magic of PCR. It amplifies a piece of DNA within a complex mixture. The specificity is provided by base pairing to a specific region by these primers. So let's go ahead and talk a little bit more about what goes on in a PCR reaction. So let us imagine that this here is a close-up of the region of the genome or the complex mixture of DNA that I'm targeting, and I'm going to label the 5' and 3' ends. And here's the magic here. The magic lies in the fact that these primers here are actually going to be, this one's actually going to bind here. And this is the 5' end of the primer. As you remember, DNA is anti-parallel, and this is the 3' end. This here is the 5' end of my second primer, and this is the 3' end. So what's going to happen is after the primers bind, and we add a polymerase and nucleotides and appropriate conditions for polymerization, we are going to copy this piece of DNA here. We are going to extend this primer. And during the first round of reaction conditions, we don't know exactly where this extension is going to stop. How long it will proceed for is partly a function of what we call the processivity of the DNA polymerase that we're using to do the copying. In the next round of the PCR reaction, you've probably read about thermocycling. What's going to happen next is this piece of DNA is going to be, that's the 5' end, that's the 5' end, that's the 3' end, that's the 3' end. These double-stranded DNA molecules are going to be denatured. That's the 5' end, that's the 3' end. This here is the 5' end, this is the 3' end. These double-stranded DNA molecules are going to be denatured, and then when we drop the temperature and do the annealing step, we are now going to allow the primers to bind specifically to their targeted piece of DNA on the template. And so again, now we're going to extend those primers during the polymerization step. And what you notice is we've gone from 2 to 4 double-stranded DNA molecules. So for a PCR reaction, the number of cycles we do, if we call that N, the number of molecules we end up with is 2 to the N, where N is equal to the number of cycles. So a couple of things to pay attention to, please. The size of the PCR products is determined by the flanking ends of the primers, by the 5' end, by the distance from the 5' end of the forward reverse primer and the 5' end of the forward primer. All the PCR products are extended primers, and the amount of product we get is going to increase very rapidly because it's going to increase in an exponential fashion. So now that you've thought about that, you're ready perhaps to go think about what you're going to pipette into your test tube in the laboratory.